Welcome. Before we jump in, I want to take a second to outline what you, the viewer, can expect this time around. In my experience, math is typically viewed as a toolbox, something filled with daunting mountains of equations, definitions, and logic. But the point of this video is to offer an alternative point of view, that math is also an intuitive visual subject where profound results and insights exist outside of that realm of numbers and formulas. So to do this, I'll tell you about one of my favorite mathematical constructs using one of my favorite culinary constructs. As always, we should begin with some background. So recall that a circle is this geometric object, but we're going to think of it this time around as this unit interval, this closed interval where the two endpoints are attached to one another. This creates the one-dimensional sphere S1 and just so happens to also be the one-dimensional torus T1. What's a torus? Glad you asked. This is a donut-like object, but we're not thinking of the full donut, we're just thinking about the glaze on the glazed donut. So not the fluffy interior, just the icing. To build this object, we can go ahead and use a filled square to start, and then go ahead and identify the opposite sides as equal. So red sides are the same and blue sides are the same. And yes, the orientation of this identification does matter, but we'll leave this for another time. So I'm going to go ahead and leave you with the actual identification with the orientations, just so you have the correct reference. This is T2, the torus. Now, you can also think of it as a product of two circles, but again, another video. So the question I want to ask is, well, we've done this for one dimension, we've done this for two dimensions. What does a three-dimensional torus look like? Well, easy. Let's just go ahead and bump up the dimension by 1 and repeat the same construction that we did for the two-dimensional case. Right? So let's consider, instead of a solid square, let's consider a solid cube, and we're going to identify opposite faces as being equal. So we build this solid cube, and then say the front and back faces are exactly the same locations. The top and bottom faces are the same. And then, of course, the left and right faces are the same. So we'll reiterate that here. These are just identifications. The left and right side, the front and back, the top and bottom, you think of this as a game of Portal. These are the same sides, the same points. But what does this have to do with bagels? Now, our usual bagels are these solid tori. And, well, I'll tell you right now, these are not the only ways to build bagels. These are easiest for bakers, but we can have 2-hole bagels, 3-hole bagels, however many holes you want. And they are all useful to a certain degree, but it's important to remember that these are all solid constructions. So, why are they interwoven, as the title of the video suggests? Let's kind of play with some structure element here. This is going to play more to the visual aspect of math that I was telling you about at the beginning of the video. So we'll build a one-dimensional skeleton, if you will. We're going to take a whole bunch of line segments and connect the center of the cube out to each of the faces. But remember, each of these faces, opposite faces, are equal. So if we take just that skeleton and remind ourselves that front and back, top and bottom, left and right are all the same point, we can kind of connect these guys together, and it will be useful for us to thicken up this skeleton so that it's kind of a fat skeleton. It's a thick graph. Now, this will take a second to draw. So let's think about what we're going to do with this. We're really considering not just what this object looks like, we're going to consider what the complement of this region looks like inside of the cube. Now, this construction does get a little ugly, and you can see I even messed up the over and under crossings at one point, but I just want to stress that this is kind of ugly, but this is just how that graph sits inside of this cube. So I ask, is there a nicer way to draw this? Sure there is. Well, the thing that we want to think of this as, I mean, topologically, right, as a general shape, this is a 3-holed or genus 3 solid torus, a bagel. Right, so now that we've figured out what this core looks like, we want to see what the rest of the cube looks like without it. So let's go ahead and push that skeleton from the center down to that front right corner of the solid cube. We'll go ahead and consider what's left here in a moment, but remember, because of the way we've identified the faces of the cube, all we get are effectively 3 edges of the cube. And the remaining space, we can go ahead and complete the same construction we just did. We'll make that one skeleton, thicken it up, and we'll have another three-dimensional or three-holed bagel. So sure, we have not one, but two genus 3 bagels. One of them being blue, the other being goldenrod. And the new bagel fills the complementary space of the cube. Their powers combined, they are a tangled mass of bagels that produces the three-dimensional torus. So as I'm building this, bear in mind that we started with the goldenrod skeleton, but this skeleton, because of the identification of the faces of the cube, all of those edges are really the same, opposite to one another, as are the points, the corners, and then we have the blue skeleton in the middle, so they are filling in complementary spaces to one another. And you want to think about these as being glued together. This is a non-trivial gluing, but they are glued together. And this constitutes what is called a genus 3 Heegaard splitting of the three-dimensional torus. And with that, we'll go ahead and end this video. I hope I've given you a glimpse into a different facet of what math can be. That it's not just this mountain of equations and definitions and logic. If you're interested in Heegaard splittings, I have a few more videos on my channel discussing them from basic principles, so feel free to check those out. I'll link them here at the end of the video. If you have any questions or comments, feel free to leave them at the bottom of the video here. Otherwise, thanks for watching.